I'd like to start my presentation with reference into our team of experts from aerospace and mechanical engineering department, optics here in UOA, as well as from NASA Ames and NASA JPL. My talk will be about current state of the art and some ideas of where can we go in terms of Mars exploration using airborne vehicles. And let's start from the success of Ingenuity Mars helicopter. It was first flew for 2 minutes. And then next step, I want to do some analysis, engineering analysis, what happened actually. If you look at the mass breakdown, out of 1,700 grams, batteries took 270 grams, rotor 850 grams. Then you look for the payload. There's no payload there. There's no room for the payload. Well, it's interesting to check what was the rotation rate of blades, and they are up to 0.7, Mach 0.7. Doesn't want to. So no payload, Mach 0.7, meaning very high speed, rotational speed, and the linear speed approaching a flight regime, flow regime, what we call transonic, when we do expect a lot of problems and issues overcoming drag and associated with this high power requirements. So we know that for the Mars atmosphere with very low density and with that high speed, there are two problems coming together. The problem of low Reynolds number with high viscosity and problem of high Mach number with high compressibility. And unfortunately, we don't have much of knowledge on this kind of flight conditions. So we need to work very hard pushing to get forward this science and technology. And we are doing that. But while we're doing that, we don't want to wait. So what we can propose, some engineering ideas that may help even this today or these days to start flying more effectively on Mars. One idea is, again, from this table of masses. Batteries, 270 grams. Imagine we took it out and put that payload in. Well, but then we need a power, still need a power in communications. So we connect a drone, a helicopter with the ground station. It pretty much has as much of energy as available on the ground station. There's one solution, and it could be developed further even now, these days. So one more time, we have the class of vehicles that powered and controlled via a tether, a cable attached to that tether from the ground-based power source. It will enable the flight, not 2 minutes, but most likely hours. Well, how about other applications? Of course, this technology will enable exploration of regions on Mars that otherwise would be inaccessible. Go to Valles Marineris. Everyone wants to go to Valles Marineris. And with the power of tethered drones, you can do that. As you can see, you can go fly up and down, still having power source attached to connected to the multi-copter or quadcopter, whatever it is, with oblique view videos and all kinds of sensors that attach to the quadcopter. You can do some interesting science observation. Okay, so that was about helicopter technology. As we know, on the Earth, it's most of the time applicable for the short distances, relative short distances. You want to fly further, you want to fly far, you have to go with the fixed wing airplanes. Well, again, still the problem with the low Reynolds number and a high speed of flight. You want to to overcome the problem of low density, you have to fly very fast. Very fast means, again, approaching high Mach number, high speed of light compared to a speed of sound. Again, we have that problem of interactions, viscosity, and compressibility. And of course, the additional weight that will carry the airplane in forms of engines or motors will further make the problem even worse. What we propose, I mean, obviously what should be proposed, use of solar energy and use of wind energy. And we have those in significant amount, enough to do flights. So traditionally, sailplanes and gliders that we use and utilize this the wind energy, but they would utilize what we call thermals and updraft, vertical flow of air to do spiraling. And if you're lucky, you find that piece of atmosphere, you can utilize it. However, what we think that we should do, and what we've been working for a while now, we want to utilize horizontal winds, much more powerful and in all kinds of forms. We have wind shears, we have jet streams, planetary boundary layers, orographic winds. All those kinds of atmospheric unsteadiness can be utilized for the flight of sailplane. But for that, we need different ways of planning flight dynamics and flight mechanics. If you look at wind riding by albatross, this is the first maneuver that we tried, and it worked very well on sailplanes. So now, instead of just staying in air, staying in one point and trying to spiral, you have to do some advancing flight in a gradient wind developed by atmospheric boundary layer. Well, there is another thing. There is another maneuver that we, not just us, but people come up with, and these are loitering and looping and orbiting along the trajectory that is inclined with the direction of the wind. So what happens here with the interaction of the shear layer that develop on the lower part of this profile, you can actually extract energy and increase velocity or speed of the sailplane. And it can be constantly increased up to, again, this magic number of Mach 0.7. So again, no motors, no nothing, just sailplane, just aerodynamically nice shape. You throw it with zero velocity at the beginning, and then you get up to 220 meters per second at the end of the orbiting that is shown here, which can be used for the slingshot maneuver to get some altitude from 0 to up to 2,000 meters. Again, no external sources of energy. Now, in this video, we want to demonstrate that orbiting. You can see here a mount, and the wind comes from the right, and therefore there will be developed turbulence and circulation on the left, on the leeward side of the mount. And see how this sailplane starts flying. Along the plane, on the in-plane incline with respect to the wind, slowly but surely starting from 0, and at the end of the flight, you can have as much as 210 meters per second. Again, it's free, no outer source of energy, and this is how fast it can fly. And we go to the next one, and this is the example that we pulled from our experiment in Double Crater and Flagstaff. Again, similar situation, you have wind coming from the right, and then pull up over the ridge, creating updraft. So this conventional standard static soaring. But on the left of the ridge, you will have dynamic soaring opportunity, because there you have a shear of the wind, and therefore what is necessary, just put a sailplane, the correct trajectory, inclined with respect to the wind direction. So On the left, you see the camera showing from the board of the sailplane. But on the right part, you will see a trajectory, how actually this flight projected on the surface. On the left, as you can see, that is the dynamic soaring. Then the kick-off motor, there's motor there. And go to the right side of the ridge. And there you conducted a conventional static soaring. Well, of course, there are all other kind of technologies well developed on the Earth, and we can apply them with a certain modifications to Mars condition. And blimps are readily available, although they should be much larger sizes. But of course, the very effective way of application of the balloons would be not only for the loitering or anchoring on the cliffs or sites of interest to perform long duration size experiment, but also create joint missions either with sailplanes or with the drones, when actually using Brody system for docking and relaunching of those airplanes. You can, again, develop concept of operations interacting with balloons, with other type of airplanes. Well, to summarize, again, I would like to tell you a little bit of our current developments and the work that we are doing, mostly on all kinds of vehicles, at least 3 kinds of vehicles that are balloons and drones and then sailplanes. And we do have the issue of low density and associated with that low Reynolds number interactions with compressibility at high flight speed. Among the community, we do have different groups working on theory. And we believe that in addition to theoretical studies, we need to fly and fly as much as possible in Mars surface environment experiment, Mars-like surface environment experiment, including desert landscape and then canyons and then craters. And we did fly on the double crater Flagstaff at 8,000 feet. We did go to Camp Robertson, California, and we flew there at 20,000 feet. But our dream, go to Spaceport America at 100,000 feet. Why is the dream? Because it's not that easy. It's not that cheap. It's very expensive. Nevertheless, at 100,000 feet, we will have a density, atmospheric density, is about the same as on Mars. So all kinds of issues that we have with the technology can be verified and validated there. Thank you.
Thank you very much. Do we have any questions? I have one. If you're going to go to 100,000 feet, would that be like a balloon deployed?
Yeah, we do this technology already in place. We use helium-filled balloons, actually meteorological balloons, because sailplanes are quite light. Yeah, we launch them, deploy them, and fly.
Oh, okay.